Okay. So now let's look at linear regression assumptions. You hear the textbook explanation of what makes linear regression useful, or they might say that these are the assumptions of linear regression, but really a way to translate that is to say any model is a summary, right? A mean is a summary, a variance is a summary, correlation is a summary, and a regression is a summary, right? A slope is a summary of what a trend looks like. Doesn't mean that's the trend, right, in the data. It's just a parsimonious way of looking at relationships. Well, it might be the trend, but there are data points off the trend that are that might need to be taken into account as well, and depending on your research question. So linearity is an assumption with respect to the terms in the model. And I added with respect to the terms in the model, that's an important phrase. Linear regression doesn't mean that the relationship necessarily has to be linear, right? Because if you have a quadratic term, like one of these rainbows, guess we have a double rainbow here, like one of these rainbows, you have the relationship between x and y is quadratic. Well, you can put in an x squared term and model that just fine in linear regression, right? So it's linear. The formula is linear in the parameters, and you can add a squared term or an interaction and so on. We'll get to that. So that's one assumption. Homoscedasticity is an assumption. It's nice when the distribution of the data is roughly the same across the regression line. And the reason is similar to the reason in ANOVA. Remember, in ANOVA, you wanted homoscedasticity. You wanted the variance within each group. The assumption is that they're equal. And that's a similar idea here, is that the conditional variance, when you slice on a value of x or a set of x's, then the residual variance of y is supposed to be equal. Something like what you see where it says normality of the residuals, right? If you just kind of eyeball it, you're like, well, that's, more or less the variance is roughly the same across values of x. So here you in the middle panel, you have heteroscedasticity. You have much more variance in y for larger values of x than for smaller. You might want to do something about it. You can do a weighted least squares kind of approach to equalize those variances. Often it doesn't make a big deal, particularly in terms of the line itself. It might affect standard errors. So, really, I think from a practical perspective, plotting your data and understanding it is important prior to running any analysis, as I will dig into. And if you have a fan shape, if your heteroscedasticity is, that's a hard word to say, by the way, if it's extreme, you might want to resort to a weighted regression or some analyses that might take care of that. Just like if you had extreme skew, you might want to consider remedies for that, because your residuals may not be normal if your outcome variable y is skewed. So I can't cover all that in this talk, but just to say that we like to check for these assumptions in case there are severe violations. One obvious example of a violation is what gave rise to attention in organizational psychology to multi-level modeling, is that if you don't model the fact that people are within groups, for example, teams or departments, and if each team or each department is different in certain ways, then it's a mistake to treat each person as if they are independent, because their data depend on which team they're in or which organization they're in. And you want to model that dependency to get a more intelligent summary of your data, essentially. So that's an obvious example. There are other examples as well. Time points within person would be another example, right? You wouldn't want to, if everyone was given a Fitbit and you recorded their activity over time, you wouldn't want to treat all the data as if each data point was independent. You would want to say, oh, these are my Fitbit data, for the last week. These are Fred's Fitbit data for the last week. And you'd want to model within person trends and so on, and not pretend the data are independent. So that we do that to essentially say, well, once we apply the multi-level model, then the errors for that model are hopefully independent or more independent. Regression also assumes the predictors are free of measurement error variance. That's almost certainly never the case, especially in psychology. So maybe that's what makes us take all models with a grain of salt, right? No models are correct, some models are useful. That kind of notion certainly applies because our assumptions are not ever perfectly met. Of course, we want measures with as high reliability as we can get to be, get more signal, construct-related signal rather than bias or noise. But measure development is an obvious precursor. Good measure development is a precursor to running your regression or any statistical summaries.